Okay, sir.
Sunny sir, please begin.
Yes, sir. Yes, sir. Okay. Welcome, everyone. Thank you for joining us for today's webinar. My name is Karnel Singh Saini, and I am the Senior Lecturer in Aeronautical Engineering Department, PIETDS at Parul University. Today, we are presenting a webinar on instrument flight rules versus visual flight rules, presented by Mr. Vijay Ravlani, sir. Just a little housekeeping before we get started. If you have any questions during the presentation, please type them to my number 97236158001. I repeat, it's 97236158001. I'll bring them up during the presentation and we'll also have a time for question and answer session at the end. So now without further ado, we will turn the time over to Mr. Vijay Ravlani sir, our presenter today, who is a senior analyst in app programming in BA Continuum India Private Limited, having great knowledge and expertise on the subject. So, without further ado, I request you, sir, to please start your webinar. Thank you.
Okay, thank you, Colonel, for introducing me. So, yeah, good afternoon, friends and faculties. So, first of all, I hope, uh, Colonel sir, if some noise is
Just a
coming,
minute.
can you be on mute?
Sorry, sir.
Like background noise is coming, someone can be on mute.
Yes, yes. Just a minute. Sir,
Yeah,
just wait on.
yeah, sure.
Sir, just a minute.
Sure, sure. Yeah,
What you can do is, sir, you can start. I'll
yeah,
just call him.
yeah, sure. You're able to see my screen, right?
Yes, sir. Yes,
Okay,
for sure.
so yeah, thanks, Colonel sir. So, good afternoon, friends and faculties. First of all, I hope everyone is staying safe and taking utmost precautions these days in the time of pandemic. Okay, so yeah, before starting for today's webinar, I would like to give a quick background of myself. As Colonel Sir introduced me, I am working as a senior analyst apps programmer in BACI. And what Colonel Sir didn't introduce me as is like I was his batchmate in BE Aeronautical Engineering SVIT. We passed out aeronautical engineering in the year of 2012. I was placed in Tata Consultancy Services from campus recruitment, and coincidentally today I am completing 8 years of my professional career. That is, yeah, I was placed on in TCS on 4th October 2012 and completing today 8 years of my professional career. It has been a roller coaster ride, and I hope for the coming years will be. So yeah, when I was pursuing aeronautical engineering, I never thought that I will eventually work for an IT organization. But it's just that it came in my way. I accepted it with open hands. I pursued it and I excelled it, and I am here now. Okay, so when Colonel Sir asked me about this webinar, I thought not to take any webinar on something which is currently I am currently working on, like that is IT, because that might not be relevant to you. You might not be able to relate it what you are pursuing. So thought of going back and take some topic which is related to the core aeronautical, and that might be helpful to you in your near future. So today, what I'm going to talk about is, as my screen shares, it will be about flight rules, and I'll be discussing about what are the types of flight rules under which an aircraft can fly, and when aircraft will fly under which flight rule, and what does the individual flight rule means. Okay, so as my screen says, we have two kinds of flight rules. As the name suggests, IFR and VFR, it is instrument flight rules, and second one is visual flight rules. So, as the name suggests, visual flight rules is something when any aircraft is flying or under flight when by taking its reference of speed of its position or where it is heading to by just outside uh, visual things like if he is passing by some terrain or if he is passing by over a river or something, means whatever he sees or he or she sees outside the aircraft, based on that if he is flying aircraft we can say it is flying under VFR, that is visual flight rules. So exactly quoting what US FAA, that is US Federal Aviation of Administration says, rules and regulations established by FAA to govern flight under conditions in which flight by outside visual reference is not safe. In that case, it has to mandatory take the IFR, that is instrument flight rules. So IFR flight depends upon flying by reference to instruments in the flight deck, not by just looking outside the aircraft. And it navigates with the help of various avionics equipments which are fitted in the cockpit of the aircraft. So in simple terms, if we say a pilot is flying based on references what he or she sees outside the plane of navigation, height from terrain, we can say that the flight is following the VFR flight plan. These conditions where flight can operate under VFR, that is VFR flight plan, are known as VMC, that is visual meteorological conditions. For example, we can consider all training aircrafts or small aircrafts like Cessna majorly follow these VFR flight plans. But when we talk about long route aircrafts, that is like flights going from one country to another, or for that matter, maybe from one continent to another continents, pilots cannot just see outside when they are flying thousands of feet above the some ocean or where they are currently on just by looking at the ocean. So at that time, how they will know that where they currently are or where they are heading to. So these kind of conditions where VFR flight plan cannot be engaged, at that time it is mandatory for the aircraft to engage the IFR flight plan. That is, it will navigate based on the instruments or different avionics that are fitted inside the cockpit of the aircraft. One more term we should be discussing about here is, before going further, is controlled and uncontrolled airspace or controlled and uncontrolled zones. So what is it? So as the picture represents, so it's like controlled areas or control zones are that space or that dimensions of the airspace where the ATC, that is air traffic control, can provide the services. The uh, the level of minimum thresholds or minimum clearance required for the flights can be minimum when they are flying under controlled areas or controlled zones, because when the aircraft is in control area or control zone, that is the least most two areas shown in the picture, at that time they are guided by the external entity ATC control tower, and they can guide the aircraft based on the flight route. So this is the controlled airspace, and whenever the ATC or air traffic control is not able to guide the aircraft over its position or where it is heading towards, at that time it is known to be aircraft is known to be flying in the uncontrolled airspace or uncontrolled zone. So this is about uncontrolled zone, and uncontrolled zone is further divided into two parts, that is air routes and airways. So what is air routes and airways? The top two parts what you see in the picture. The air routes are like whenever the flight is cruising at its maximum altitude. So that is the air route. And airway, whenever a flight is coming into its cruise height or exiting from its cruise height, that means it is ending its takeoff procedure or starting for its landing procedure. Those that particular limit or air zone is known as airways. Okay. So proceeding further, we will see now about what are visual meteorological conditions under which a flight can opt for the VFR flight plan. So this is the pictorial presentation of various visual meteorological conditions. So considering the topmost part of the picture, that is when the flight is flying above 10,000 feet above average mean sea level. So what are the minimums that, what are the minimum thresholds that the aircraft should be having? If it is flying above 10,000 feet, it should always have at least of 8 kilometer of visibility in front of it, and it should always have 2 kilometer of clearance from the bad weather clouds. When the same flight is coming below 10,000 feet of average mean sea level, what are the various meteorological conditions for the VFR flight plan? In that condition, it should always be 1000 feet above the average mean sea level, or you can say 1000 feet above the terrain, not the mean sea level, 1000 feet above the terrain. It should always have 5 kilometer of the visibility. Yes, the visibility reduces as the cruise flight level reduces. So when it was above 10,000 feet, the visibility limit should have been 8 kilometer, which now reduces to 5 kilometer. And yes, the vertical clearance should still remain 1000 feet from the clouds. So these two things were when the flight is operating under uncontrolled airspace. That is, there is no guidance provided to the aircraft with the help of outside entity, air traffic control or control tower. So when it is now in the control zone, as we saw in the previous slide, these thresholds can even reduce. Okay. So once the same flight comes into the controlled air zone, this distance of visibility still remains 5 kilometer, but the clearance from the cloud, that is vertical clearance, can reduce to 500 feet, and still the horizontal clearance from the any bad weather clouds should still remain 2 kilometers. So this is all about visual meteorological conditions. If a pilot knows in advance that whatever flight route or wherever from he or she has to go till wherever he or she has to go, if the conditions will be met in these conditions will be one of these, then it can operate under VFR, visual flight rule. Otherwise, not. What now we'll see about IFC, that is IMC, that is instrument meteorological conditions. So whatever conditions are outside of this diagram, that means, for example, a flight flying below 10,000 feet of mean sea level, if its visibility, if during the en route, if its visibility is going to be reduced any kilometer less than 5 kilometer, then it cannot flight under VFR. And in that case, we can say that it is not a visual meteorological condition. In that case, it has to opt for the instrument flight plan. So those conditions outside the visual meteorological conditions are known as IMC, instrument meteorological conditions. Now, in that case, IFR will be engaged. So whenever IFR is being engaged, different instruments or radars or beacon receivers come into the picture, or different procedures comes into the picture whenever IFR is being engaged. So as the diagram says, these are the 6 key points whenever IFR is being engaged. First thing is IFR clearance. This is the clearance. This is something which clearance aircraft gets from the ATC before its flight. Second and third thing is ground-based beacons and GLONASS, that is Global Navigation Satellite System. These two things are majorly. Just a second, 1 second. These two things are majorly helps the aircraft for its en route. So whenever this basically navigates, helps the aircraft in navigation of the aircraft. The third or fourth thing is ILS, localizer and glide scope. What it is and what it meant and why it is used, we'll see in the coming slides. Then fourth thing is marker beacons, and the last thing is SID and STAR, that is standard instrument departure route and standard arrival routes. Again, we'll see in uh, further details in the coming slides. So talking about obtaining clearance, so the first point of IFR, that is clearance. It can be termed as the craft in short form, and craft comprises of 5 things. So as it says, like clearance limit, route of flight, altitude, frequency, and transponder. We'll see each and everything uh, based on a sample clearance that an ATC provides to an aircraft in the next slide. Okay, so by quoting a sample clearance, it is exactly like this what a sample clearance looks like. So just quoting what a clearance is, Air Canada 301 Los Angeles clearance delivery cleared to the Calgary International Airport via the government for departure, shafter transition, then as flight. Maintain 5000, expect flight level 340, 5 minutes after departure. Departure frequency 124.30 and squawk 7201. Okay, this might seem an alien language to us, but this is how an exact clearance what an aircraft receives from the ATC before it engages IFR. So let's break this clearance into various parts, 5 or 6 parts, and understand what this clearance means. So the first thing is aircraft 301. So what is it? It is you. It is the aircraft. It always the ATC calls you with the Air Canada flight name. The what is the flight name under which you are flying. Second thing is Los Angeles clearance delivery. That's the controller identifying themselves. That is the ATC themselves. They will usually only identify themselves once only, not in the further conversations. Third thing is clear to the Calgary International Airport. So this is the first part of the aircraft, the craft clearance. This is your clearance limit. They have cleared you all the way to the Calgary Airport. The third thing or fourth thing is via the government for departure, shafter transition, then as filed. Now this is the you can say a flight plan which is indicated in the SID, standard instrument departure. What is SID? We'll just see in coming slides. So this is a flight plan already mentioned in the SID that following this particular route, the aircraft has to leave the gates and go to the approach point. The departure point to the runway. Then next point is maintain 5000, expect flight level 340, 5 minutes after departure. Again, this is the altitude clearance. It is again we can break it into 2 parts. Maintain 5000. This is the initial climb altitude. So this is the altitude defined by ATC for the aircraft under any circumstances, flight cannot go beyond this particular limit. That means during its entire en route, the flight cannot go beyond 5000 feet. This varies from different aircraft to different aircraft and from different countries or different locations to different locations. Then the next part is expect flight level 340, 5 minutes after departure. So this is not mandatory, but this only comes into the picture whenever the aircraft loses its communication with the ATC for any XYZ reason. So this is something which ATC tells that you should expect your flight level should be 340 feet after the 5 minutes of your departure. Note, this is only if you lose the radio communication. Also, again, as we saw about maintain 5000, this also varies from different regions to different regions. Next part is departure frequency 124.30. This is the departure frequency. This is the controller you are expected to contact once you are airborne. In most cases, the control tower will tell you when to contact this particular frequency. For example, if you lose the communication with the tower, at that time, you should contact to this particular frequency for further communication. Okay. The last thing is squawk 7201. So this is a transponder name, or you can say a transponder signature, which is unique for each aircraft flying. So this particular transponder name is assigned to your particular aircraft and it is unique. Okay, so this is this is the transponder with which for XYZ reason you are lost, means your connections with everything, means ATC is lost, or you are not able to reach the frequency what it was given 124.30, sco- using this SCOC 7201 transponder, the external radars will be able to identify your location. So this is the mandatory, this is the first thing an aircraft pilot should do, is to feed this particular code in its transponder in the aircraft. Okay. Okay, this is all about the craft clearance. What next? Okay, after the clearance, the aircraft or the ground controller guidance will guide the aircraft towards the runway via taxiway. Okay, then control tower will give the sign off for the aircraft to go ahead and take off. Third thing is clear airspace or airway of 10 nautical miles. We saw in the previous slides that what is airway or what is airspace. So clear airway of 10 nautical miles means whenever flight is about to take off, it should be having 10 nautical miles in front of it clear. That means no aircraft should be in the vicinity of 10 nautical miles whenever the aircraft is about to take off. Okay. Next thing is, okay, the aircraft will be using different kinds of avionics, that is ground based beacons, GPS or GLONASS or ILS system. What are all these avionics system? We'll see in the upcoming slides. So this is the procedure after the clearance. Once the aircraft receives clearance, what is the next step? Okay. Okay, so next thing is ground-based beacons. So these are the beacons used to make the flight plans, or these are the beacons helps the aircraft during the en route or for the navigation. So the type of beacons which are used in the for navigation are VOR beacons, or you can tell them as a very high frequency omnidirectional range. So these are type of short range radio navigation system for aircraft, and the aircrafts are enabled with the receiving units of these VOR beacons based on the signals that the receiver in the aircraft will receive from this VOR. It can check where currently the aircraft is or where it is heading to. There is a way, there is a huge network of these kind of beacons spread across the globe, using which the aircraft will know its position and where it is heading to. So these VOR beacons, as the name suggests, very high frequency, operates in the very high frequency band, and that is generally from 108 megahertz to somewhere around 117 or 18 megahertz. In between, it transmits the signal which will be intercepted by the aircraft. Okay, over the period, the use of this VOR beacons has been reduced. I mean, it's like you can say they are becoming obsolete because of the old technology, and the number of VOR beacons over the globe are also reducing because they are becoming, as I said, they are becoming obsolete. So, what is the next instrument or the system using which an aircraft can know its position or the en route, how it will know where it is going, where it is heading? So that will be GLONASS, that is Global Navigation Satellite System. It is slightly different from our conventional mobile phones GPS. So as the diagram says, now consider, we'll see how GLONASS works. Consider you are point X and it is 1 kilometer from point 1. Okay, so you know that you are 1 kilometer from point 1. That means you are somewhere on the circle with the radius of 1 kilometer and the center is point 1. So same way, if you know that again your point X is 2 kilometers from point 2, so again you can say that you are at another circle which is of the radius 2 kilometer from point 2. So this means you are somewhere on the intersection of those two circles. So this way you will be narrowed down to the 2 points where you currently are. This is about your how conventional GPS might work. Okay, using the trilateration method. You might have heard about word trilateration in movies or serials. So that's how this works. So okay, you are now narrowed down to 2 points. Usually point 1 and point 2 will give you 2 points. Possibility that you can get only one point of intersection of these two circles, that means you are at that point, but not always. So that's why you will need a third reference point. And once you have the third reference point, that you are suppose 3 kilometers from a circle with radius 3 kilometer from point 3, and that will give you the point, one single point, that means where you are currently. Now, in this is about a two-dimensional space. This might not be always true. I mean, this not will be true definitely when we are talking about the aircrafts, because it is flying in the air, which is three-dimensional. We cannot be just relying on the three satellites. So when we're talking about GLONASS, that is Global Navigation Satellite System, it will be okay. Let's see how GLONASS will work. So consider a flight is flying, which receives a signal that it is 100 nautical miles from satellite 1. Okay, in that case, we can say 100, the aircraft is somewhere on the sphere. Now, not on the circle, quote me, it is on the sphere with the radius of 100 nautical miles, of which the center point is satellite 1. Same way, considering satellite 2 in the picture, it is 200 of nautical miles from the satellite 2. That means it is somewhere on the intersection of those two spheres. And if you imagine, the intersection of those two spheres will give you a circle. So your aircraft is somewhere on that particular circle. Now, increasing one more satellite here, which is a satellite 3. Again, considering that you are 300 nautical miles from that satellite 3. So earlier you were having a circle. Now again, one more sphere intersects it. So now your location will be narrowed down to the 2 points, that is intersection of the circle and the intersection of the third sphere. Now, still note that we are using these three satellites also. We don't know our exact position because we are still narrowed down to 2 points, not the 1 point. Now, coming to the satellite 4. If we have a satellite 4 into the picture, that means it will coincident will be with the one of the point which we got from the intersection of three satellites. So that's how the GLONASS, that is Global Navigation Satellite System, will work. So an aircraft flies based on the signal which it receives minimum from the four satellites, not from the three satellites. Okay. Okay, so that's how the GLONASS works. Okay, just a quick recap. We saw different stages of the IFR, that it receives the clearance from the ATC. It takes off with the 10 nautical miles of clearance of airway. It navigates till its destination airport with the use of either VOR or ground-based beacons, or using this GLONASS, Global Navigation Satellite System. What next? Our aircraft wants to land also now. Okay, so while landing, the system that is engaged or that is used is called the instrument landing system. It comprises of mainly three things, that is localizer, glide scope, and marker beacons. Marker beacons we'll see in the next slide. In this slide, we'll see what the localizer and glide scope is, and what their functions is. Okay, so as the picture says, you can see that the localizer is always located at the far end of the runway. Ideally it is located at the both end of the runway, but whenever aircraft is coming for the approach, it will be intercepting the signal that is coming from the far end of the runway. So considering in the picture, if the aircraft is coming from the left hand side, it will receive the signal from the localizer on the located at the right hand side of the runway. So how localizer works? Localizer works mainly by it transmits two frequency lobes, that is 90 hertz and 150 hertz, and where these two frequency lobes are exactly coincident, and so that particular line of approach is known as the on course. On course, it is like it is mentioned in the aircraft that if that intersection line is matching, if it is exactly on the intersection line, then the flight is said to be on course for the landing purpose. Okay, and otherwise if it is receiving either more of the 90 hertz or more of the 150 hertz, then accordingly the aircraft or the pilot will adjust to be on the on course for the landing. Next thing is glide scope. Glide scope works exactly on the same principle, but it's just that the lobes of the frequency are just a bit tilted, or you can say it's like slightly not as aligned as the localizer were. It is like, okay, with the different orientation, I will say. So where is glide scope located? Okay, again, like localizer, it is located at the both end of the runways, not exactly at the end of the runway, but somewhere around 750 to 12,000 feet, or you can consider as a average of 1,000 feet from the start or end of the runway at the both ends. And again, unlike localizer, it is not located at the center line of the runway. It is somewhere uh, offset of the runway, around 400 to 600 feet offset of the center line of the runway. Okay, again, this transmits two frequency lobes, 90 hertz and 150 hertz, and the intersection of these two lobes, perfect intersection of these two lobes in the aircraft will give the pilot uh, the exact approach angle of 3 degrees for the landing. Okay, this was about localizer and glide scope. Next thing coming in the picture for ILS is the marker beacons. So what are the marker beacons? Uh, these are the marker beacons. Okay, we saw localizer and glide scope will give the center line and the approach angle of the aircraft. But how will the aircraft know of the distance pending from the runway? So for that, these marker beacons are used. Usually there are three marker beacons. Usually there are, I'll say two marker beacons, not always three. I'll just let know where the three marker beacons come into picture. So usually there are two marker beacons, outer marker beacon and middle marker beacon. So what is the significance of these marker beacons? So whenever the flight is okay, outer marker beacon is like it's situated at almost like 4 to 7 nautical miles from where the runway starts. It is like you can say, okay, when the aircraft will fly above the outer marker beacon, the marker beacon receiver in the aircraft will give its indication in both visual and oral sound. The visual signal will be like a blue signal, and the oral sound will be of you can say of 400 hertz frequency. And if you know what the Morse code is comprised of dot and dash codes using which any characters or anything can be written. So in that Morse code form, the the pilot in its headset will receive the continuous dash codes. Just bear with me, I'll just play that kind of visual and sound. So this kind of outer marker beacon indication will be, okay, let it complete. Okay, this kind of visual indication and oral indication will be uh, indicating the pilot that it is somewhere now at around 4 to 7 nautical miles from the landing, from the aircraft, from the, sorry, runway. Next thing is middle marker beacon. So whenever the flight is flying over the middle marker beacon, again the receiver of the marker beacon in the cockpit will give again an oral sound as well as the visual sound, visual depiction. The visual depiction will be of amber color, and the oral sound will be of around 1300 hertz frequency in the headset of the pilot. And the indication will be in the amber color, and its distance will be almost around 3,500 feet, or as it says 1 kilometer from the runway threshold. Just bear with me again. This is how the sound and the visual representation of middle marker beacon is. So it will be showing them, it will be oral sound of marker beacon in the Morse code form. It will be dot dash dot dash. And the third is the inner marker beacon. Again, it will be visual signal. The marker beacon will show the white signal, and the oral sound of 3000 hertz frequency will be heard in the pilot's headset of around 3000 hertz. and that means that aircraft is around somewhere between 200 to 1500 feet from the runway. So how that will be heard and visualized is like this. It will be the Okay, it will be in the continuous dot forms if we see with respect to the Morse code. Okay, so as I discussed, the third inner marker beacon may not be mandatory for all kinds of airports, but it will be mandatory only based on the airport. So there are three kinds of ILS system we can say, or three kinds of airports based on which the number of marker beacons is defined. So that we'll be seeing in the next slide. So basically there are three kinds of airport: Cat 1, Cat 2, and Cat 3, based on what kind of ILS that airport is engaged with. So as the pictorial depiction shows that once, if at all, decision height is not lower than 60 meters, that means if my flight is somewhere around above 60 feet, still I have scope of correction of my final approach or my angle, and the visual range of runway is not less than 5 feet 550 meter, then the airport is categorized under cat 1. If these limits are reduced, that means the decision height reduces to less than 60 meter or more than 30 meter, that means aircraft is still allowed to correct its course of action in this in between this height above the runway, and it is having the runway visual even not less than 350 meter, then it is categorized as cat 2. And further, if the visibility or decision height reduces, well, then we call it as a cat 3. So in Cat 3 kind of aircrafts, the inner marker beacon is mandatory. In Cat 1 or Cat 2, it is not mandatory. So Cat 3 is like, you can, in simple terms, you can say like Cat 3 is like the more riskier airports the aircraft is going to land. Just giving an example, if you search on YouTube something about Paro International Airport in Bhutan, that is kind of cat 3. You can see how difficult the landings on the that particular airports are, so that's why it is categorized in the cat 3. So this is brief about cat 1, cat 2, and cat 3 kind of aircraft. Okay, next thing is okay, SID and STAR. So SID term we discussed in bit in earlier slides as well. So what is it? Standard Instrument Departure Route. So SID route is something. These are the stipulated routes already filed in the aircraft books, using which the aircraft will leave the ATC and it will go for the takeoff. So that particular route from which a flight will start for the IFR flight, that particular route is known as SID route, that is Standard Instrument Departure Route, and its completely opposite is STAR, that is Standard Arrival Route, or in some countries it is known as Standard Arrival Standard Instrument Arrival as well, SAR route also. Okay, so this is completely the opposite of SID. So same way, when the aircraft is exiting from its en route and about to exit the IFR flight, so that all procedures are logged in the STAR routes, or you can say STAR books. So using that particular routes, an aircraft will exit the IFR flight, and once it is landed, the flight can turn off the IFR, and further it will be navigated by the control tower, or you can say the ATC, local ATC on that particular aircraft. So that's about SIDS and stars. Okay, so yeah, that's how it's like IFR flight is engaged using ground-based beacons and global navigation. It is en routing towards the destination. and using ILS localizer, glide scope, and marker beacons, uh, the flight is landing. ILS is like a very good system. That's why it is being used for over the years now. And using ILS, it's like even pilots nowadays can fly, land in with even 0 kilometers of visibility as well. And this is about the SIDS and STAR, that how a flight will enter in the IFR flight and how it will exit the IFR flight. Okay, so yeah, that is all I had to say about various IFR and VFR flight rules. So that is all about from my end. Now, any questions from your end are welcomed.
Okay, Vijay sir, thank you. Now we will go ahead and take some time for questions now.
Sure, sir.
Just a reminder, please be
Yep.
sure to type your questions to my number. My number is 97236158001. I repeat, it's 97236158001. Okay, sir, it looks like we have one of the question for
Yes.
you.
Yes, sir.
Sir, how VOR works for IFR rules, basically.
No, that's what visual operating rules cannot be applied for IFR. That means, like, see, as I shown. Okay, let me go back into few slides. Okay, so these are the visual meteorological conditions. Sorry, the question I missed. Your question was VOR, right? Sorry,
Yes,
my
sir.
bad. Okay, yeah. So VOR is like it is transmitting very high frequency of the range what I told, and these frequency it's like digitally rotating. Consider this is a VOR. You can see different. There are various what you can say. Antennas which are transmitting this particular frequency. Digitally, this particular VOR rotates this signal with the frequency of almost 120 hertz. That means uh, every 120 in single second there will be 120 rotations of the signal from the antennas. So consider there are two VORs at position 1 and position 2, and aircraft is receiving VOR signals from one VOR and two VOR. So each VOR will have its unique frequency assigned. So if it is receiving frequency from one and two VORs, so that's how it will be communicating. Okay, this is this particular distance from this particular VOR, and it is at this particular distance from second VOR. So that's how it. For example, it is going towards a destination which is close to the VOR one and not the VOR two. Gradually, if it is intercepting the signal more from VOR1, so it can say that it is towards the end route. But if it is somehow receiving VOR signal from VOR2 more, that means it is definitely not the correct path. So that's how the flight plan includes each and every second of the flight en route, that at which particular point what should be the amount of frequency you should be receiving from different VORs above from which the aircraft will fly.
Okay,
I
sir.
I hope I didn't confuse, or am I clear?
No, no, sir, it's clear.
Thank you.
Now I'm having second question with me.
Yep.
Sir, can you bit elaborate the difference between our conventional mobile GPS and GLONASS?
Yeah. Okay. So let me go back to that slide. Okay, this slide is something based on which trilateration method works. Okay, I'll not go in detail on this particular thing, but let me go to the next slide. Okay, consider let's go to the three satellites. Okay, we saw right this intersection of three spheres will give us the 2 points. Now, uh, we all know that GPS mainly works on the three satellites. If we are receiving the signal from three satellites, we can say that we know where we are currently. But there is a point hidden behind it. Whenever the three satellites intersect, as I told, we get 2 points of intersection. But using complex mathematical formulas and all, if we see, one of the point will be always very close to the Earth's surface, whereas other point will be not really close to the Earth's surface. It will be somewhere above the Earth's surface. Now, whenever we talk about our conventional phone GPS, mobile GPS, we are expecting that definitely our GPS receiver will be very much close to the ground. So at that time, our mobile GPS will discard that particular intersection point which is above the Earth's surface, and automatically we will be having only one point of intersection which is close to the Earth's surface. That will be our mobile GPS receiver. But that's how our conventional GPS works. But when it comes to an aircraft is meant to be on the ground as well as in the earth surface, on the above earth surface, or in somewhere in the three-dimensional airspace. So that's why for aircraft, if it is receiving 2 points, we cannot say where it is. So that's why in GLONASS the fourth satellite comes into the picture, using which we narrow down further those two intersecting points into one particular unique point. So that is a key difference between our how conventional GPS and our mobiles work based on the three satellites. But why there are four satellites required for GLONASS navigation for the aircraft to work precisely. So that's how the difference is between conventional GPS and aircraft GLONASS. I hope it is clear.
Yes, sir. Thank you. Now, one more question is there, sir. How can we differentiate instrument flight rules but with visual flight rules? What is the basic difference between the two?
Okay. Ideally, see, whenever, as I discussed about VMC and IMC, that is visual meteorological conditions, and so there are certain limits that about 10,000 feet it should have 8 kilometers of visibility and all. So whatever XYZ parameters are for VMC, if not even single parameter m- is met by a flight. For example, consider an aircraft is flying from Mumbai to Delhi, or let's say from Mumbai to USA. So there will be some oceans coming into the picture. So using whenever a flight is, the pilot cannot just see outside the window and looking at the ocean thousands of feet. It cannot say where it is heading towards. So at that time, avionics comes into the picture, transponders come into the picture. So those kind of flights where the pilot cannot just see outside the window and it can say where it is flying or where it is heading. That kind of flights cannot will not the flying under VFR will not be safe. And in aviation field, safety is the utmost priority for any XYZ matter. So that's why these VFR flights are mainly used for the small training aircrafts. That's why we see trainings and all are not happening on a mass scale in the bad weathers, because these kind of Cessna aircrafts and all, these are not well equipped with all the aviation instruments which a commercial flights are equipped with. So that's why Cessna aircraft cannot fly under IFR. It will fly only VFR, and that is the key difference between VFR and IFR. That if it cannot fly in VFR, it has to be in the IFR. So like it's like a not a clear difference between IFR and VFR. It's the difference between VMC and IMC, and if it is not meeting VMC condition, it has to fly under IFR. Um, Hope I am clear or confused. Same.
Yes, sir. You are clear.
Yeah,
Uh, I'm having one more question, sir. Can you put a more light on controlled and uncontrolled airspace once again?
sure. I'll go back to that slide.
Yes, sir.
Okay. So controlled and uncontrolled airspace. Okay, nice thing. Okay. Uh, Okay, you would have all noticed at most of the airports, we have a control tower. So whatever things aircraft or a pilot cannot see from the cockpit whenever it is on aircraft. The ATC can see further than the what a pilot can see. That way, that means at that particular time, ATC can give more guidance to the pilot rather than whatever pilot will see from the inside. So that's why it is. That's why control towers. That's why the name says control tower. So it's like it will be having more control on the aircraft based on the what it can guide to the aircraft rather than when it is in the airborne. So that is the limit in the limit or in the dimensions of the airspace under which a control tower can guide the aircraft, that is known as a controlled airspace. And whenever the aircraft is having its avionics now, so it's consider it is far away or 50 kilometers away from the airport or the control tower. At that point of time, the aircraft will be under more capability of knowing its position or where it is heading about rather than what control tower can provide it the location. So that particular airspace is known as the uncontrolled airspace. It's like okay, don't go by the name uncontrolled airspace. It's just because the control tower cannot guide the control. It is still controlled. It is control with the app with respect to all the avionics and all the pilot has in the aircraft, but it is uncontrolled because the control tower cannot guide the aircraft at that particular time. So that's why the nearby vicinity of the airport, when it is about to enter the approach or when it is exiting the departure, so till that point it is known to be in the controlled airspace, and whatever is outside it is known as the uncontrolled airspace.
Okay, sir. So that's all what questions and answers we have.
Okay,
Now, thank you very much, sir, for sparing your valuable time, and thank
sure.
you, everyone. We appreciate you being here. And now I would like to present an appreciation certificate to Mr. Vijay Ravlani, sir, on behalf of Parul University. So, Vijay, sir, I would request you to please stop sharing your screen so that I can share mine.
Sure, I'll just stop. Yeah, go ahead, Karan sir.
Okay, sir. Okay, sir. I hope it is visible to all. So, I would like to
Yes,
congratulate you, sir, and thanks for sparing your precious time to the students of Parul University. And on the behalf of university, I would like to give you certificate of appreciation from our side. Please accept the same, sir. And thank you very much for providing your precious time.
okay. Thank you, Colonel sir, for giving me an opportunity just to leave my IT world behind and go back into the aeronautical world. Okay, once again, thank you for giving me this opportunity of presenting this webinar. Yeah, thank you.
Okay, okay, sir. Thanks a lot.